T2 space is nothing but a topological space is said to be T2. A topological space is said to be T2 if and only if for any 2 points belonging to x not equal to y, there exists how many open sets? 2 open sets such that x belongs to u, y belongs to v, and u intersection v is null. That is the definition of T2. So we want 2 open sets separating 2 distinct points x and y. 2 disjoint open sets. Very, very important. Now we shall take up the next theorem. The next theorem on T2 space is this. If F is a continuous mapping and onto from x tau to y tau dash, x and y are both topological spaces such that x is compact and y is T2. That is, domain is compact and the codomain is T2. Then we have to prove that the F is a closed mapping. What do you mean by closed mapping? So we have to prove that F takes closed sets to closed sets. Okay, now we shall prove this. Proof of this theorem. Very, very easy proof. So what is given, we'll write down. Given F is a mapping from where to where. They have given X is compact, Y is T2, and they have given the mapping from where to where, X to Y, okay, which is dash and dash, that is continuous and onto. They have given it as continuous and onto. We have to prove that this F from X to Y is a closed mapping. We have to prove that F is a closed mapping. Okay, so let us take any closed set. Let G be a closed set. Let G be a closed set in X. Let us be a closed set in X. We have to prove that f of G is closed in Y. We have to prove that f of G is closed in Y. Okay. So since G is closed in X, and what is X? X is compact. And we have a theorem. A closed subspace of a compact space is compact. So therefore, G is compact in X. G is compact in X. And what is the function F? F is continuous. F is continuous and onto. F is continuous. Since F is continuous and onto, what is F of G? F of G is compact. We have a theorem. Continuous image of a compact space is compact. So using that theorem, right? F of G, the image of the compact space, is also compact. So f of G is compact. F of G, where it will be in Y, and Y is T2. The given Y is T2. And we have a theorem. What is the theorem? A compact subspace of a T2 space is closed. So using that theorem, we get f of G is closed. F of G is closed. G was a closed set in X. We proved f of G is closed in Y. So therefore, F is a closed mapping. F is a closed mapping, hence the theorem. A small theorem and very, very easy theorem. So this theorem is over. Now we shall take up one more definition and then a theorem. A definition is this. What is the definition? Let us look at the definition. A sequence xn in a topological space x tau converges to a point of x if and only if for all open sets of x, for all open sets G of x, there exists some n naught, a natural number belonging to n, such that xn's belong to G for all n greater than or equal to n naught. That is, a sequence xn converges to a point x in a topological space x tau if and only if for all open sets G of x there exists an n naught belonging to natural numbers n such that the xn's belong to G for all n greater than or equal to n naught. That is the definition of any sequence converging to a point x. Converging to a point x. Now using this definition, we shall prove a theorem. Theorem is this. A convergent sequence in a T2 space. We're going to prove a convergent sequence in a T2 space has a unique limit, but the converse is not true. We have to prove that in a T2 space, suppose the topological space is T2, then we should prove that every convergent sequence has how many limits? Only one limit. That is unique limit. But the converse is not true. So first we prove the convergent sequence has unique limit if the topological space is T2. Then we shall prove the converse is not true. Okay, so proof. So first we'll prove the necessary part. So let x tau be a T2 space. Let x tau be a T2 space. And let us take a convergent sequence. Let xn be what sequence? Convergent sequence. Where? In that topological space X, which is T2 given, we have to prove what? To prove that this sequence xn has unique limit. We have to prove that this has unique limit. Okay, that means only one limit. This sequence has only one limit. That we have to prove. Suppose this sequence has two limits. Suppose xn converges has two limits. Say x and y, which are distinct, and x not equal to y. Say we have two limits for this xn and x not equal to y. Now, since x not equal to y, and where are these two, x2, x and y? Two limits in x. And what do we know about x? X is T2. So what should happen now? This implies there exists two open sets. We'll call them as G and H, such that x belongs to G, first open set, y belongs to H, and they are disjoint equal to null. Okay, let us call this disjointness as 1. Equation 1. Okay, and what else we know? The sequence has two limits, no? Now, using the definition of the convergence, xn is converging to x, xn is also converging to y. Let us take the convergence of the sequence. Okay, yes. So okay, since xn is converging to x, since xn is converging to x, xn is converging to x. What is the definition of convergence? This implies that for all open sets G of x, okay, there exists an n naught such that xn belongs to G for all n greater than or equal to n naught. And what is our G here? G is an open set of this small element x. Okay, so this implies that there exists some natural number, we'll call it as n1, belonging to n natural number, such that xn's belong to G for all n greater than or equal to n1. This is because G is any open set of x and xn is converging to x. Also, xn is converging to y. We have taken two limits, remember? So xn is converging to y. And what is the open set of y? H is an open set of the element y. So what will happen now? So this implies there exists another natural number, we'll call it as n2, belonging to n, such that xn's belong to the open set H for all n greater than or equal to n2. Can you guess the next step now? Let n naught be equal to maximum of n1 and n2. Maximum of n1 and n2. So that, why we are taking this maximum? So that, what is the next step now? Xn's belong to G and I want the common elements. That's why I'm taking the n naught. So xn's belong to H for all n greater than or equal to n naught. That implies xn's belong to both, no? So G intersection H. G intersection H for all n greater than or equal to n naught. Are we getting a contradiction? This is a contradiction. Why this is a contradiction? Because we have G intersection H is null. This is by 1. We have called it as 1, no? By 1, we got this is equal to null. This is 1. So we got a contradiction to this 1. So what is the conclusion now? So therefore, I cannot have two limits, only one limit. So therefore, every convergent sequence where in a T2 space has how many limits? Unique limit. So first part of the theorem we have proved. Now we shall go to the second part. Now what is the second part? Second part says that the converse is not true. What do we mean by the converse? What is the converse? Okay, we shall put the converse is not true. So we have to prove the converse is not true. So what do you mean by converse actually? That is if every convergent sequence has unique limit, has and unique limit in some topological space, in some topological space x tau, then this x tau need not be unique limit. If every convergence sequence has unique limit in x tau, we have to prove that that topology need not be T2. Need not be T2. We shall give an example. We shall give one example. For example, we shall take one example. We shall take an example of co-countable topology. Consider co-countable topology. Co-countable topology. What do you mean by co-countable topology? What is our x in co-countable topology? So let x be an uncountable set. Uncountable set. And what is the topology here? Tau consists of all the subsets of x such that A complement is countable. A complement is countable. This is co-countable topology and we have proved, we know this. Okay. Now, so what we have, what actually we have to prove? We have to prove that if, every convergent sequence has unique limit, but the topological space should not be T2, need not be T2. So we have taken one example. The example is this. So we are going to prove, okay, we can call it as first step or whatever is the number you can give. First, we'll prove that this topological space, x tau, the co-countable topology is not T2. The first step, we are going to prove that this is not T2. Okay, suppose it is T2. Okay, if it is so, if possible, suppose this co-countable topology is T2. What is the meaning of T2? This implies that for all pairs, x comma y belonging to x such that x not equal to y, there exists how many open sets? Two open sets, u and v, such that x belongs to u, y belongs to v, and u intersection v is null. Suppose it is T2. I have written the definition of T2. Okay. Since u is open, u is an open set containing x, no. So since u is open, will imply that what is u complement? U complement is dash. So u complement is countable. Because we know any set is open if and only if its complement is countable. Similarly, since V is open set, what is its complement? Is countable. We have two countable sets. What about their union? Union V complement. Union of two countable sets is countable. Okay. And this set is nothing but U intersection V whole complement is countable. What is U intersection V? U intersection V is null set. Null set complement is countable. What is null set complement? Null set complement is X is countable. Is it so? This is a contradiction. Why we got a contradiction? Because our X in co-countable topology is uncountable. Uncountable. So we got a contradiction. So what is the conclusion? Therefore, this co-countable topology, X tau, what? Is not T2. is not T2. Okay. Now what remains to be proved? In the next step, we have to prove that every convergent sequence has unique limit. So in this case, TPT, to prove that every what sequence? Convergent sequence has unique limit. We shall prove that every convergent sequence has unique limit in which topology? In this example, co-countable topology. Okay, in co-countable topological space. Topological space. Okay, so let us take a convergent sequence. Let us take a convergent sequence. Let xn be a convergent sequence. Let xn be a convergent sequence. Let us take a convergent sequence. Let xn be a convergent sequence. Let us take a convergent sequence. Okay. We shall prove that this convergent sequence, we shall prove that this convergent sequence xn is a constant sequence. We shall prove that in the co-count topology, every convergent sequence is a constant sequence. Okay, and constant sequences have definitely unique limit. And we are going to prove that in this example, that is the co-countable topology, we are going to prove that this convergent sequence is nothing but a constant sequence, right? Hence unique limit. Now suppose it is not constant sequence. We shall prove that constant sequence. Okay, done. Suppose it is not constant sequence. Suppose it is not constant sequence. Case 1. Suppose xn is not constant sequence. In that, I'm taking case 1. Case 1 is this. Suppose xn tends to x. Xn tends to x and xn not equal to x for all n. See, I have a limit, but the limit doesn't belong to the sequence. It is different from the elements of the sequence. Okay, suppose this is case 1. See, I'm assuming it is not a constant sequence. So one case is this. And we shall take up this next case later. Okay, suppose xn doesn't not equal to x for all n. Okay, let us define A as the set of the elements of the sequence xn, the set of the elements. What elements? Distinct elements, the set of distinct elements of the sequence xn, the set of the elements, distinct elements of the sequence xn. Okay, and the set of the elements of the any sequence will be either denumerable or finite. So definitely or clearly A is dash. Can you guess? Countable. A is countable. Okay, and A is countable. A is countable now. So what is A complement? A complement is, can you guess? Fast. A complement is open. Because we are in the co-countable topology, right? And in the co-countable topology, complements of countable sets are open sets. So A complement is open. So we have an open set here. And see, since xn not equal to x for all n, does x belong to A? Since xn not equal to x for all n, very important, for all n, clearly our x will not be belonging to A, because A is nothing but the set of the elements of the sequence. So where it will be then? So x will definitely belong to A complement. And A complement is open. So we got an open set of X. We got an open set of X. And Xn is converging to X. No. Okay, let's take it. Xn is converging to X. Xn is converging to X. So for all open sets, the definition of the convergence of any sequence in a topological space. So for all open sets G of X, there exists N naught belonging to N such that Xn's belong to G for all N greater than or equal to N naught. This happens for any open set of X. And here we have an open set A dash. So therefore, since A dash is an open set of the element X, what will happen now? So open set. So there exists N naught belonging to N such that Xn's belong to A dash. A dash is open set, no? So A dash, in the case of G, I'm writing A dash. For all N greater than or equal to N naught. Is it a contradiction? See, I'm getting Xn, some Xn's, okay, belong to A dash. Actually, Xn's are coming from where? This is a contradiction because all Xn's belong to A. For all N, all Xn's are coming from A. And I'm getting here some Xn's. For all N greater than or equal to N naught, Xn's belong to A dash. Definitely this is a contradiction. So we got a contradiction here. That means what? That is the sequence Xn, a convergent sequence converging to a point, okay, and Xn not equal to X for all N, this statement cannot happen. Cannot happen. This cannot happen. Remember, we have to prove this is a constant sequence. So in that, I'm assuming it is not constant sequence. So I'm taking the first case. First case is this. If this happens, and if this happens, I got a contradiction. So definitely this cannot happen. So this cannot happen. So what is case 2? Case 2 is this. Case 2. Suppose case 2. Case 2. What is the next option now? Case 2. Not a constant sequence. What is the other option? Suppose Xn tends to X, convergent sequence, okay, and Xn equal to X for some N.